So when we're thinking about science, we're going to be doing a lot of measurements. We're going to be doing a lot of calculations. And in both of those processes, it's going to be important that we have the correct number, but it's also going to be important that we have the unit associated with it. Because if we just have that number by itself, it's got no context. We don't actually know what it represents. So if you think about 42, the answer to everything, if we just have 42, it could be anything. And then if we put the unit, 42 miles is much different than 42 kilometers or 42 grams, 42 seconds, 42 whatever it may be for that particular unit. There are a few exceptions where we'll just have a number by itself. So when we talk about like equilibrium constants, they're unitless, and a few other things are unitless. But for the most part, we've got units, and they're important to include to give that context. And then they're also important because they um, can help us solve certain problems. If we're not totally sure how to set something up or go through a certain calculation, we can sometimes just use the units we have, think about where we need to get to, and help that kind of dictate the path that we take. So with chemistry, with science in general, when we're working in the lecture room, when we're working in the classroom, make sure that you're not just writing down a number, make sure that you're writing down the unit with it. Sometimes if you're filling out like a data table or something, it's already got the unit implied in the table because it'll say like final volume in milliliters. In that case, it's telling us what the unit is already, so you don't need to write it again. You can, doesn't hurt, but for the most part, we want to make sure that we're always including those units. And with the units, it's important that we include it. It's important that we also have a agreed upon understanding of what those units represent. That's going to be important, especially with scientific research. One, if people use different units, it's going to be really difficult for scientists to communicate with one another. They're going to have to do a lot of conversions just to figure out what those numbers represent in that different unit. And we'll do a little bit of that unit conversion later on in this chapter. But it's also going to be important that when we're talking about a specific unit, that everybody has an agreed upon understanding of what that is. So if you think about a unit like the foot or feet, if every city just based that on the length of a different person's foot, then that unit is essentially meaningless because people in different places are going to have a different understanding of what that represents. So we've got to have a defined system. And in science, the system we use is known as the International System of Units. And we generally just call that the SI units or the SI system. And with it, there's specific units that are kind of like the basic unit for whatever that measurement's going to be. So you can see a handful of them here. Length, the SI unit, so the base unit essentially for length is going to be meter. Mass is going to be kilogram. Time, seconds, temperature, Kelvin. But in other cases, we may use different units. So especially with the metric system, we can throw on prefixes. So you can see meter here is just the most generic length measurement in terms of the metric system. But then with mass, now instead of gram, we have kilogram. So a kilogram is going to be 1,000 grams, and we'll see that as well. But we can use the prefixes in the metric system to change the scale of these units if we need to. So sometimes if we're working with a large substance, we might use kilograms. When we're working in the lab, though, we don't generally have to use too much of any chemical. So we'll often use gram instead. We'll just use the regular gram. And then with temperature, sometimes we use Kelvin, sometimes we use Celsius, but we pretty much never use Fahrenheit in science. But we'll go through some of these individually too. But with these metric prefixes, you can see a whole bunch of them here. Just help us allow us to change the scale of those units. So like I said, a kilogram is 1,000 grams, because a kilometer, that prefix kilo, just represents 10 to the third. Conversely, if we look at something like centi or milli, 10 to the negative second, 10 to the negative third, that means we're going to have 100 centimeters in a meter, or 1,000 millimeters in a meter. So these are just going to allow us to change the scale of those different units. And when we're writing the units, so you can see an example here, centimeter, we've got meter, which is just the M, but then to indicate that it's now centimeter, we just put a C in front of it. Same thing, deciliter becomes DL instead of just liter. Kilometer, KM instead of just meter for the M again. And when we're looking at the unit conversions, we'll kind of go through a little bit more on how we can make those conversions. But the metric system is nice because unlike the imperial system where 12 inches in a foot, 3 feet in a yard, 1,760 yards in a mile, there's no sort of set system in terms of how we make those conversions. There's different numbers relating all of those different units. Whereas with the metric system, it's just factors of 10. So when we're making the conversions with these metric units, as long as it's one metric unit to another metric unit, we can just essentially move the decimal over rather than having to do division and multiplication and actually figuring out what that new value is going to be. The metric one just allows us to move that unit because there's 100 centimeters in a meter, there's 1,000 millimeters in a meter, there's 1,000 kilograms in a gram, or 1,000 grams in a kilogram, excuse me. But we're just going to be moving the decimal as long as it's metric to metric. But when we're looking at different units, length, like I said, meter is going to be the SI unit for that. And with it, some of them are kind of unique definitions. In the past, a meter was defined as 1/10 millionth of the distance from the North Pole to the equator. Now we have it as 1/299 millionth, 299, 792, 458th of the distance light travels in a second. So if we're looking at light traveling in a vacuum, it'll go that many meters in a second. So they kind of use that as the definition. Not super important for our course. But again, we can look at these prefixes and just see the relationship between those different units. So 1 unit, a centimeter, much smaller than a meter. So it makes sense that we have to have a whole bunch of those to equal 1 meter. And then a millimeter, even smaller, need even more of those to equal that meter. But now a kilometer is a longer distance, so now we need a lot of those meters to equal that kilometer. So depending on which direction we're going, is going to determine exactly sort of which way we move that decimal. But again, we'll look at those when we look at the unit conversions later on. Mass is the kilogram, so you can see used to be based on a couple of different samples, but to try to make it more concrete, because with some of these samples, they actually do change slightly. Now we just have it based on physical constants. But again, that definition's not important. We just want to recognize that kilogram's the SI unit for mass, but we can get rid of that kilo and just use grams if we want to measure something that's smaller. And we can use kilograms, we can use grams to both measure big and small things, but sometimes it's easier to change that unit just so we get nicer numbers to work with. So if you think about it, if we had something that was 25 grams, pretty easy number to work with in grams, we could convert that to kilograms and have a decimal, and it would still be the same value. It's just kind of depending on what exactly are we doing, what's easiest to use in some case. Sometimes if we're doing a specific calculation, a specific formula, we need one particular unit. And that's going to be one reason we want to be able to make those unit conversions. But with the next unit, temperature, so we'll talk about all three of these here. Kelvin, Celsius, and Fahrenheit. Celsius and Fahrenheit, you're probably the most familiar with. Fahrenheit, of course, because we live in America. That's the one we use the most often. And I actually think that does have useful applications. So when we're thinking about environmental temperatures, it's pretty easy to just think about, okay, 0 is really cold, 100 is really hot, and then anything in between, we can kind of just get that nice scale. And the relationship between Fahrenheit and Celsius, at least the change in temperature, if we change the temperature in Fahrenheit 1.8 degrees, that's a 1 degree change in Celsius. So I think Fahrenheit is also easier to see things like fevers. That same change in temperature is going to be a larger change in temperature in Fahrenheit, so it's sometimes just a little bit easier to see. And then, like I mentioned, the environmental temperatures, I think, make a little bit more sense with Fahrenheit. And that might just be because I only ever lived in America, so that's just what I'm used to. But if you think about Celsius, a lot of those temperatures are going to be more compressed just between like -10 degrees Celsius and 40 degrees Celsius. So it's going to be a smaller range. It's going to be harder to get a easier understanding of the changes in those conditions. But Celsius is going to be the one that we use quite a bit, especially when we're measuring things in the lab. If we have a thermometer, we're always going to read it in Celsius. And you can see on these scales, Celsius is also easier in terms of science a lot of the times, just because it's based on water. So 0 degrees is where water freezes in Celsius, 100 is where it boils, whereas we have 32 and 212 for Fahrenheit. So those are just kind of weird numbers. So Celsius has that advantage. And then Kelvin is the exact same thing as Celsius. It's just offset by 273. So if you look here, water freezes at 0 degrees Celsius, water freezes at 273.15 Kelvin. And then absolute zero, the lowest possible temperature where motion ceases to exist. So solids, as we mentioned, still do vibrate slightly. But once we get them to absolute zero, that vibration ceases. So with Kelvin, that's what the scale is based on, absolute zero, the lowest temperature, whereas Celsius is just based on water freezing. So they're just offset by 273. But a 1 degree change in Celsius is the same as a 1 Kelvin change. And then also note with Kelvin, we don't say degree. So you don't have to say 273.15 degrees Kelvin. It's just Kelvin. So there's no degree there, unlike with Celsius and Fahrenheit. And that's why with these ones, we've got that little degree symbol to the top right of the value. And like I mentioned, we'll use Celsius a lot in the lab. That's the one that we use to measure things. Kelvin sometimes is what we need for specific calculations, because Kelvin never goes negative. So if we plugged in a negative value for temperature, like we could potentially have for Celsius, that could screw things up. But with the temperature, if there's a specific case where we absolutely need Kelvin, I'll always make sure to highlight that as we're kind of going through that material. But for this course, you can pretty much just throw out Fahrenheit because I can't think about any case where we'll actually use that one. And then volume. So we've got volume just as the amount of space that an object takes up. Talked about a little bit when we started with matter. So matter has mass. Matter also has volume. And with it, this is going to be what's known as a cubic unit, just because it's going to be three-dimensional. So if you think about length, it's only measuring in one direction. But now when we're looking at volume, we've got length times width times height. When we're looking at something like a cube, you can see the formulas for some of these other regular shapes. And because of that, our unit itself, or one of the units we can use, is going to be a cubic centimeter, or a cubic meter, cubic whatever that we're measuring that in. And the reason for that is if we think about this as a cube here, let's just say each of these sides is 1 centimeter. The volume of this would then be 1 centimeter times 1 centimeter times 1 centimeter. So 1 times 1 times 1, just going to give us 1. But when we're doing multiplication or division, whatever we do to the value, we have to do to the units as well. So it's really 1 times 1 times 1, but it's also centimeter times centimeter times centimeter. And that's why a potential unit here would just be cubic centimeter. Sometimes, especially with like hospital TV shows, you might hear the term cc. We need 10 cc's of whatever. A cc is just going to be a cubic centimeter. It's just another kind of abbreviation or shorthand for it. We'll never use that one, but just in case you do hear that and wondering exactly what that's referring to, it's just referring to this volume unit of cubic centimeter. But a cubic centimeter is also just going to be equal to a milliliter. So milliliter is a measure of volume. Liter is the SI unit for that. So a milliliter would just be 1/1000th of a liter. But these two units are going to be the exact same thing. They represent the exact same volume. And with the volume, sometimes if we look again, these are like regular shapes, things that are neatly defined. We've got like sharp edges in the case of a cube, and just well-defined structures, which allow us to have equations to actually calculate the volume of these objects or these shapes. But in some cases, we're going to have irregularly shaped objects. So things that we can't just measure the length and width and height of, or any of those other equations that we just saw. And in that case, we can still determine the volume of it. It's just a little bit more, maybe not even complicated, but it's just a different process. And that process is just going to be the volume by displacement. So one example of this is there was I don't know if it's a real story or if it's just like a fable or myth, whatever. But I think it goes something along the lines of a king or queen has a crown. They want to determine if it's actually gold or whatever it's made of. And in order to do that, they need to determine the density, which I have right here. So I'll talk about that as a second, and then I'll go back to the displacement one actually. But density is just going to be a measure of how tightly packed something is. So you can see here, we could pretend each of these smiley faces was a atom or a molecule of a particular substance. And what we're going to see as we go from gas to liquid to solid, for the most part, water will be an exception, but for the most part, as we go from these phases to the next, we're forcing these atoms or molecules closer together. So we're making them more dense, and that's why for pretty much every substance, the pure solid of whatever that substance is going to be would sink in the pure liquid. Water is a unique example again, though, because the solid's actually less dense than the liquid. That's why we have ice floating on water. But for the most part, pretty much every other substance is going to follow this trend where it becomes more dense because we're just forcing all of those atoms or molecules closer and closer together as we go from gas to liquid to solid. And with density, it's just going to be mass per volume. So one common unit for it is grams per milliliter. That's the one we use in the lab a lot because that's the scale of the quantities that we have. But we've also got that equation, mass over volume. We can think of it as this triangle here. So we've got three corners, and you can kind of just go in alphabetical order, put the letter near that corner. So just going left to right, D, M, V. So when we're trying to solve for one of those pieces, think about it, it's an equation with three variables. If we know two of them, we can solve for the third one. So if we're trying to solve for density here, and then also just note we put lines in between each of these. If we're trying to solve for density, that means we need to use mass and volume. So mass is on top of volume. That's why we're going to divide it. So density is equal to mass divided by volume. But now if we're trying to solve for mass, we've got that on top. So we've got density and volume next to each other. So that means we're going to multiply those two together. Density times volume will give us the mass of that object. If we know how tightly packed something is, and we know how much space it takes up, we can figure out how much it actually weighs. And with this, let me get the drawing tool out. So let's just say grams per milliliter, and then just milliliter. So those could be our units. We could have different units there. I'm just going to use those ones because that's what we use the most often in the lab. But with this, and I'll talk about it a little bit later when I go through the sig figs and how we do calculations in science, because it's a little different than what you might do in math. But we have to include the units, and then whatever we do to the units in terms of multiplication and division, or whatever we do to the value in terms of multiplication and division, we have to do to the units as well. So it makes sense that density is going to be grams per milliliter because we're dividing mass by volume. So grams divided by milliliter just gives us that. And then the mass one, grams divided by milliliters times milliliters, those milliliter units are going to cancel. That's why we're just left with grams on top when we multiply density and volume. And then the third one, if we're solving for volume, if we know how much something weighs, we know how much space it takes up, we can do mass divided by density. And in that case, grams divided by grams per milliliter. Remember, dividing a fraction by a fraction is really the same. So if we have this, is really the same as multiplying by the inverse. So we could have grams times, we'll flip that bottom fraction then, milliliters over grams. Now grams are going to cancel. We're just left with that milliliters unit. So if you just remember density is equal to grams over milliliters, or mass over volume, really, I should say, because it doesn't have to be those units. You could always just rearrange it to solve for whatever that missing piece is, or you can try to use this pier or triangle sort of setup to just think about the positioning of those. If they're above and below, we're doing division, but with density and volume, since they're next to each other, that's why we multiply those to solve for mass. But to go back now for the volume by displacement, like I was mentioning, there's some story, I don't know how true it is or if it's just completely made up, but somebody had a crown, they wanted to figure out if it's actually the substance that it was claimed to be. So they wanted to use the density of it to compare it to the known value. If it's doesn't match up with the density, it's just not that substance. So with the crown though, unlike these shapes, we can't just measure the sides, do a calculation and get it. So in order to figure out the volume, they had to come up with a different way. And the story goes that the person that was trying to determine this was really struggling, couldn't think of anything to do. And then they set up a bath for themselves, went to get in the bath, and then as they sat in the water, they noticed that the water level rose. And then that gave them the idea for this volume by displacement. I believe the story continues that they then got out of the bath, ran down the street yelling Eureka, because they figured it out. But the basis of this volume by displacement is just thinking about, we have some graduated cylinder, so we can measure the volume of water here. We've got 4.80 milliliters, or 4.8. This is kind of a weird one because it goes up by 0.2, but 4.8 milliliters, and that's just the water. So then when we take our object and place it in there, the water rises now to 5.6 milliliters. But if we think about it, the only difference between this water on the left and the water on the right is the fact that we now have an object in here. So any difference in these measurements is just going to be due to the volume of that object. So in this case, this little toy dinosaur thing. So with it, we've got the final minus the initial. We could do 5.6, excuse me, minus 4.8, and determine that the volume of this object is just going to be 0.8 milliliters. With this, there's a couple of things to make sure of as you're setting something up like this, is we want to make sure that the object is fully submerged. So let's say we were doing this with a pencil instead. We drop the pencil in, the water rises, but the eraser is still poking out the top. That means we're not accounting for the volume of that portion of the object. So we've just got to make sure that we've got the object fully submerged. And then also with this, it doesn't matter exactly where we start this water. So if we had a procedure that said, fill a graduated cylinder with 5 milliliters of water, place your object in there, and record the new value, we could spend a bunch of time trying to get to 5 milliliters exactly. But as long as we, as long as we record the actual starting point, so again, in this case, 4.8, the only thing we're looking at is the difference. So we could go from 4.8 to 5.6, or we could go from 5 even up to 5.8. And in either case, it's still that same change because we're just looking at the difference between where we started and where we finished. It doesn't matter exactly what those points actually are. It's just the difference between them. And then once we do have this volume, it's easy to measure the mass of an object, just place it on a balance, record whatever that value is. So we would have the mass, we've got the volume here, we can determine the density of whatever that object's going to be. And then here you can just see a few examples. And again, one of the rare exceptions up at the top, that ice is less dense than water. And that's got huge implications in terms of our survival on this planet and the survival of a lot of organisms. Because if it was the opposite, ice would sink, lakes and things would freeze from the bottom up, so they wouldn't help protect the organisms in those during the winter. And then one other thing I just want to point out here is if you look at the units, grams per cubic centimeter for these first two columns, same thing as a gram per milliliter, because remember, cubic centimeter, milliliter are the exact same. But then in this column where we've got the gases, we've got grams per liter. So just note that the units here are different. A liter is much greater than a cubic centimeter. A liter is going to be 1,000 times larger than a cubic centimeter or milliliter. So we've got much more space with these ones, but we've got just about the same amount of mass. If you think about 1 gram per cubic centimeter for water, 1.2 grams per liter for dry air. That's about the same mass, 0.2 different. But now this one is occupying 1,000 times the amount of space. And then later in the quarter, we'll also note why it's important that we measure or we indicate the temperature and the pressure that this is at. Because like we talked about with the gases, they're compressible. So if we increase the pressure, we can decrease the temperature. So if we increase the pressure, we can decrease the temperature. And then we can actually force that air closer together. We can increase the density of it. Whereas if we increase the pressure of a solid or liquid, it's just not going to change anything about it really because they're not compressible. And with the liquids, you'll notice a lot of them pretty similar here, but we've got mercury much, much higher. And then the solids, we've got a wider range there, but a lot of these metals are going to be very, very heavy, or very dense, I should say, not heavy. Heavy is just a reference of mass. Density is just how tightly packed something is. Okay. And like I mentioned, with measurements in science or calculations even, it's going to be important how we kind of divide those, or not divide those, how we report those values, how we round our answers at the end. And with science, we've got what's known as significant figures. And this helps us determine sort of the level of uncertainty in a measurement. And the only types of measurements that won't have any uncertainty at all is just counting. So if we're thinking about like a classroom, there could be 24 students in there. And as long as I have the ability to count, there's not going to be any uncertainty in that. Same thing with like chairs in the room, whatever it may be. If we can simply just go 1, 2, 3, 4, 5 and count through, there's no uncertainty in those measurements. So those are going to be what's known as exact numbers. And there's going to be one way we treat those. We can basically just use them as just a regular number like we would in math class. But when we're making measurements, there's going to be an uncertainty in those. In addition to counting though, defined quantities are also exact. So if you think about conversions like inches to feet, there's exactly 12 inches in 1 foot. It's not 12.0002 or anything like that. It's 12 right on the dot. So those are exact values. Counting is an exact number. But when we're making measurements like with the graduated cylinder here, that's going to be an inexact number. We're going to have significant figures there though to tell us how uncertain that value is. Essentially, how much confidence can we have in that measurement? So when we look at the graduated cylinder here, and graduated cylinder, it's just called that because it's a cylinder, and then graduated is just referring to the marks on here that represent those different volumes. So the gradations, graduation. But when we're making a measurement like this, there's a couple things we need to know. One, we read from the bottom of the meniscus, so don't read from where it touches the sides. We read from the bottom of that curve. But also, depending on how that instrument's graduated, determines how certain it's going to be and how many digits we should report in that answer. Because if we're looking at this, we can see each of these lines represent 1 milliliter. So we can see this is somewhere between 21 and 22 milliliters, but we don't want to just say 21 or 22 because we can always go 1 digit further than what's actually displayed on that measurement device. So in this case, since it goes up by ones, our measurement should go to the 10th place. If we also had tenths included in here, then we would go to the 100th place. So we can always go 1 digit further than what the device is representing. And that's in the case of something like a graduated cylinder. I'll talk about balances in a second. But in this case, I would say that's something like 21.6 milliliters, because if we look at the one on the right here, it's again in between 21 and 22. But to me, it looks like just a smidge closer to 22. So rather than 21.5, I'll just put 21.6. And then again, we've got the unit here because we've got milliliters. So if you want to take a moment to see if you can identify what we would report these values as. So we've got 2 different graduated cylinders. And again, we want to think about the same thing. Where's the meniscus? And then how many digits can we report based on the marks on that particular cylinder? So the one on the left goes up by ones, but the one on the right goes up by tenths. So each of those lines represents an increase of 0.1 in the case of B. And if we're looking at these, again, the bottom of the meniscus, with the first one, a little bit easier because it's right on that 24 line, but we don't want to just say 24 milliliters. we would say 24.0 milliliters to indicate that it's right on that line, basically. Because again, we can always go one digit further. So with this one here, it's in between 2.6 and 2.7. So we could say something like 2.65 milliliters. You're always going to go one digit further than what's shown on that measurement device. With balances, though, it's a little different. In that case, we're not making the measurement ourselves, really. It's the balance just telling us the output. But in that case, we want to make sure that we record all of those values, even if there is zero. Because if a balance tells us it's 15.49 grams, that means the measurement's between 15.48 and 15.50. But it could be, like I said there, 15.488, 15.494. And the big thing is going to be when the value ends in zero. So let's say we had our balance 15.50. We wouldn't want to report just 15.5. We would want to make sure we include that zero because that gives us more information. And then with it, the rules for significant figures, I'll save for the next one, actually, just because I don't have time right now to go through all this.